Thank you, and thanks, Martin, for inviting me to this talk, to this event, and happy birthday to Eric and Mike. So I'm going to talk about estimating Schatten norms in streaming model, which is still somehow different from those complexity talks. Okay, so since I'm talking about a streaming model, I need to first define what streaming model is. Okay, so in a streaming model, I consider there's a frequency vector x that is n-dimensional, first initialized to 0 vector, and then it gets updated when you're processing the data stream. So in fact, each element in the data stream describes an update to x that consists of an integer I and a real number delta, which means to add delta to the ith coordinate of x. Okay, so so at the end of the stream, you want to compute some function big F of x. Of course, the most naive way to do this is to store the entire x and update it accordingly. But that would require n space, which is huge, and could be prohibitive if n is huge. So what we really want to do is to compute f of x in small space. That means we inevitably lose some information of x, so we cannot obtain exact answer. So the algorithms are usually randomized and approximate, which means that the algorithm should output y that satisfies the constraint where y is between 1 minus epsilon times big of x and 1 plus epsilon times big F of x with a good probability. Okay. And a very common approach to this kind of problem is called sketching, which means that you don't store the entire x, you only store a summary that we call sketch of x. And in the end, you try to compute f of x from that short sketch. And more commonly, actually, all existing algorithms maintain a linear sketch. That is, your sketch y is a linear function of x. That means there exists a linear operator L, or a matrix L, let's say, such that y equals L times x. And because the algorithm is randomized, as we said above, this sketching matrix L is usually a random matrix. So why do we need a linear sketch? Because it makes the update easy. At each time, you update only one coordinate of x. So that means your x gets added by a vector that has only one non-zero coordinate. So L times this one this vector with only one non-zero coordinate is just a column of L times by some constant, and you add it to the y that you have maintained. So that's why we prefer a linear sketch. So the algorithm usually maintains such a linear sketch, and then at the end of the stream, it computes big F of x from y. Okay, so this is the model. And a lot of previous work have studied f of a particular form. That is, this big of x, big F of x, can be written as the sum of some function small f of each coordinate. And I think the most studied function is fx equals x to the pth power. And this is called an FP moment problem. And this problem has a rich research history over a decade. It goes back to 1996, actually, when the journal paper was published. And more recently, Braverman and Ostrovsky and a few others have begun to study more general f, and they obtain certain characterizations of the properties of f and the related space complexity of the of the corresponding algorithms. So basically, the vector case has now been resolved, and the most natural generalization is move to the two-dimensional case, that is matrix here. So input X represents an n by n matrix, big X, say. And still we can ask a similar problem, but this time we do not ask for functions that decompose into functions that decomposes into sums of functions on coordinates on the entries of the matrix, but functions that decomposes into sum of the functions of singular values of that matrix. Okay, and again we can consider the function fx equals x to a pth power, and this corresponds to the Schatten P norm of that matrix. Actually, if you take the sum of all singular values raised to pth power, that's the pth power of Schatten P norm. So this is also a natural generalization of the fp moment problem in the vector case. Okay, and just a side note, when p goes to infinity, the Schatten P norm goes to the operator norm of the matrix. And when p goes to 0, it goes to the rank of the matrix. Okay. And now, because I said we want to compute f of x in small space, so there are two kinds of space bounds that we usually consider. One is the typical bit complexity bound, that is how many bits you need to store your sketch y. And here we assume that every entry of x takes log n bits. That is, every entry of x is of size poly n. And because we're using sketch, another natural quantity of space bound is the sketch dimension, which is the number of rows of L if you view L, the sketching matrix, as a linear operator, or just the number of rows of L. And the sketch dimension is usually easier to work with. For instance, easier to work with. Now, if you have actually designed a sketch and you have a sketch dimension bound, so this is a sketch dimension upper bound, that naturally implies a bit upper bound if your sketch matrix, every entry of your sketch matrix has, say, log n bits or constant number of bits. Yes?
So in the case that p equals 2, you might as well think of the matrices as vectors.
I'm sorry.
If p equals 2, you show the two extremes, the infinity and 0. But if p equals 2 is a Frobenius norm.
No, right, it is. I'm not saying I'm only.
No, I'm just asking. Yeah, I'm just asking. That's the easy
right,
case
yeah,
for you.
Yeah,
that's
exactly,
all.
Yeah. So, but the lower bound is much more difficult, because one coordinate of your sketch, which is a real number, can require a lot of bits to describe. So the sketch dimension lower bound does not imply bit lower bound. And this is a somehow difficult problem. And because bit lower bound, if it does, then things can work much easier, because sketch dimension usually, the lower bound of sketch dimension can usually be argued using it's just more mathematical, using some distributions of hard instances, while the bit lower bound usually requires a communication complexity argument. So if there's a systematic approach that transfers sketch dimension lower bound to bit lower bound, then a lot of things will become easier. But still, we don't know, we don't know how to obtain bit lower bound from sketch dimension lower bound. And so in the next talk, in this talk, I'm going to talk about the bit lower bound and the sketch dimension lower bound for estimating Schatten P norm in the streaming model.
So when you're talking about bit lower bounds, are you putting a restriction on the algorithm? Is it a sketching algorithm or not?
It could be any algorithm. Yeah, but anyway, so previously I had a result that says if you assume the entries of your input is of size poly n, then basically every streaming algorithm can be converted into this linear sketch algorithm. Any streaming algorithm can be converted into a linear sketching algorithm with loss of log factor in space. And here's the result for bit lower bound for estimating Schatten norms. And previously, there was no work on this. And the lower bound inherited from the vector case because you can always plant a vector onto the diagonal of your matrix. And for p greater than 2, this lower bound is n to the 1 minus 2 over p. Now for p between 1 and 2, the lower bound was n to the 1 over p minus a half divided by log n, which comes from some embeddability result of embedding LP space into L2 space. And for p between 0 and 1, the previous result is log n bits. And for p equals 0, and the Barrier and Schwier-Gaussian proved in 2015 that the rank problem, where p equals 0, has an almost linear lower bound. That is, the bound is n to the 1 minus g of epsilon, where g of epsilon goes to 0 as epsilon goes to 0. So it's almost linear. And in a recent paper by David and me last year, we improved the case basically for p greater than 2, except that p is an even integer to this almost linear lower bound. While and we show that this near linear lower bound is tight for sparse matrices, by which I mean that each row and each column has only a constant number of non-zero entries. So this almost linear lower bound is tight for such sparse matrices. Now for yes.
When you say sparse, are they matrices that stay sparse throughout the entire stream, or only sparse at the end?
Well, it can be only sparse at the end. Okay, but somehow, I mean, this actually so this lower bound actually holds in a stronger model where you. I mean, this lower bound is actually stronger because it holds in a more restrictive model that you can update your element only once. So that makes this lower bound stronger. Yeah. OK, so for p greater than 2, the previous lower bound n to the 1 minus 2 over p is actually tight already for sparse matrices. So there was no improvement on that case on that case where p is an even integer. Okay, so so now let's see how this is proved. So first, we need to revisit Barrier and Schwier-Gaussian's result for estimating rank. So they reduced that problem to a communication problem called hidden Boolean hypermatching problem, which was first studied by Verbing and Yu in 2011. And then Barrier and Schwier-Gaussian studied that problem of a slightly modified version. So in this hypermatching problem, Alice has a Boolean vector x that is n-dimensional, such that the Hamming weight is always n over 2. That's the vector has half of its entries being 1s, and the other half being 0s. You may assume n is an even integer here. And Bob has a perfect T hypermatching M of n over T edges, where each edge has exactly T nodes. Now, for each edge, you can look at the corresponding coordinate of Alice's input x, and then you can count whether there are an even number of 1s or odd number of 1s there. So they want to determine whether for those hyperedges, the corresponding, the number of 1s at the corresponding coordinates in x is always even or always odd. And this is the hidden Boolean hypermatching problem. And Verbing and Yu in 2011 showed that this problem has an almost linear lower bound for one-way communication. That is n to the 1 minus 1 over t, where t is an arbitrary constant integer. Of course, the hidden constant in omega depends on this integer t. Now this problem has a natural graph interpretation as follows. So suppose now given an n, we create two n nodes arranged in two rows, one upper layer and one lower layer. Okay, now for Bob's input, for each t click in Bob's input, that is the edge of a for each hyperedge in Bob's for Bob's input, you create a click of size t in the lower layer, like this. Now we want to connect the nodes from the upper layer to the lower layer according to Alice's input x, which means that is if we see xi equals 1 at coordinate I, then we connect the ith node in the upper layer to the ith node in the lower layer. So now the graph looks like you have some cliques in the lower layer. Now each clique may have some tentacles connecting this clique to some nodes in the upper layer. Okay. And the problem can be rephrased as to determine whether all cliques in the lower layer have an even number of tentacles or odd number of tentacles. Okay, now this problem has an almost linear lower bound. And also, Berry and Strigosen figured out that size of maximum matching of this graph is different by constant factor in the two cases. That means estimating the size of maximum matching requires an almost linear lower bound, communication lower bound. So now, how is this related to estimating the rank of a matrix? There's a natural connection between the size of maximum matching and the rank of the matrix if we consider the Tata matrix of the graph. So what's Tata matrix? So the Tata matrix looks like adjacency matrix, but you flip the sign on all lower triangular entries. So for this matrix, because we know that it decomposes into pieces of cliques and tentacles, so okay, so the connection is that the rank of the matrix is twice the size of maximum matching. Now, what does the matrix look like? Sorry. Now you get a linear lower bound for estimating rank. Now, what does the matrix look like? So up to permutation of rows and columns, the matrix becomes a block diagonal matrix, where each block describes a piece of a clique and the tentacles connecting to it. So each block is 2t by 2t, can be arranged in this form, and that is the matrix A describes the clique, but it's a Tata matrix of a clique. That means you have 0 on the diagonal entries, 1s above the diagonal line, and -1 below the diagonal line. And dk describes those tentacles. So it's a diagonal matrix with only k1s on the diagonal. That describes the k tentacles. Okay. Now, if you look at the rank of this matrix, you can see that the rank is different by a constant factor when k is even or k is odd. Somehow this reduces to the estimating rank or the size of maximum matching of the graph. Now for the general P, we can massage the construction of the graph a little bit to the point where each clique has a random number of tentacles independent, and the number of tentacles across the cliques are independent, and the number of cliques is random even number or the random odd number. So in order to estimate the pth parallel of Schatten P norm, we can look at the pth parallel of Schatten expectation of pth parallel of Schatten P norm of a single piece, like this. Okay. And if there is a constant factor gap of this expectation between the odd and even case, then we know there must be a constant factor gap between the odd and even case of the whole matrix, because the pth parallel Schatten p-norm of the big matrix M is just the sum of piece parallel of Schatten p-norm of those small pieces. And by Chernoff bound, because you've got so many pieces by Chernoff bound, the piece parallel of Schatten p-norm should concentrate. That means the gap is preserved in the big matrix M. So basically, if we want to so this already gives us an approach to get a linear lower bound. Basically, if we can verify that the piece parallel of Schatten p-norm of this small piece has a constant factor gap, then we get a linear lower bound for estimating Schatten p-norm. So now let me show an easy example that shows you a square root n lower bound for p not equal to 2. So the linear lower bound we can obtain is inherited from the hidden Boolean hypermatching problem that gives you n to the m minus 1 over t. And if we want a root n lower bound, we take p equals 2. Now in this case, each piece is a 4 by 4 matrix. And here the upper triangle, the upper left block, 2 by 2 block, describes the clique. And so, but in this case, the clique is just an edge. So you have 1 above the diagonal, and you have a minus 1 below the diagonal line. Now you have 3 different cases with no tentacle, 1 tentacle, or 2 tentacles. So you can see with 1 tentacle, then you have 1, 0, 0, 0 that describes only 1 tentacle. And if you have 2 tentacles, then you see there are 2 ones in the block in the upper right block, on the diagonal line in the upper right block. Okay. So then you calculate the singular values. So in the case of no tentacles, you've got 2 ones. In the case of 1 tentacles, you get 2 square root 2s, and in the case of 2 tentacles, you get 4 singular values. They're like golden ratio and the reciprocal of golden ratios. So now you can calculate the expectation of the piece parallel of Schatten p-norm of the pieces. So in the even case, the number of tentacles k is a random even integer, so it takes value 0 with half probability, and it takes value 2 with another half probability. So you get the expression on the left-hand side. So basically, it's a sum of the Schatten. It's a sum of singular values, right? And times the probability half. Now for the odd case, you have only one choice. It's 1 tentacle, so you get the Schatten norm is square root 2 to the piece power times square root 2 to the piece power. Okay. Now we can show that they are not equal unless p equals 2. So for p not equal to 2, the left-hand side and right-hand side are not equal. And this gives us a gap between the even case and the odd case. Okay, and the square root n lower bound follows. Okay. And for general p, of course, we can use this construction. You can use this matrix, but somehow it's complicated to analyze. So we can actually choose a different matrix, as long as this matrix can be constructed from the clique information and tentacle information. And for p that is not an even integer, this is the simpler matrix that we choose, where you have a block of all ones in the upper left of the matrix. Below that, you append a diagonal matrix of k ones. And so if you run this in a stream, in a communication game, then when Alice sees her input, he can add dk to that matrix. And when Bob sees his input, he can add the block of all ones to that matrix. So that means the matrix can be constructed from the input of Alice and Bob. Now, for even integer p, the matrix is even simpler. You take a matrix that's 0 on diagonal line, one's off diagonal line, and then you put k1s, and then Alice can add k1s on the diagonal line. Okay. So basically, you can choose different matrices to simplify your analysis. Then in the even case, I'm not going into details of this. So in a case where p is an even integer, and the analysis boils down to an alternating binomial sum, and then you can use hypergeometric identities to simplify that sum and prove there's a gap between, prove that sum is not 0, which means there's a gap between the odd case and even case. Okay, and but there's but okay, now the deficit of this lower bound is it only holds for sparse matrices, because the graph we consider here is sparse. And more recently, some people from UPenn constructed dense graphs using Lucia-Shemeredi graphs, and they obtain a near quadratic lower bound for estimating the size of maximum matching. That means now you have a near quadratic lower bound for estimating the rank. So unsolved question is, does this new hard instance give a gap for general Schatten p-norm? If it does, then we know a subquadratic lower bound for Schatten p-norm. That means if you want to estimate Schatten p-norm, you basically cannot save any space. You have to store the entire thing. Now, this is an open question. Okay. So now I'm going to move to the sketch lower bound. So previously, the lower bound for p equals infinity, that is the operator norm, is n to the 3/2. Now it's a weird, there's a funny coefficient. And for p greater than 2, it's 3/2 times 1 minus 2 over p. And for p smaller than 2, it's square root n. That's rather weak. And for p equals 2, it's just constant number. Now, we thought that n to the 2 times 1 minus 2 over p is more reasonable bound, because the lower bound for the vector case is n to the 1 minus 2 over p. And now you're in the matrix. You're having a matrix, so it's reasonable to just have a squared lower bound of the vector case. And indeed, the 3/2 comes from non-tight analysis of the hard instance. And later, Rutgers, basically using the same hard instance, and he obtained a coefficient that is 2 in the exponent. So this resolves the case for p equals infinity. But somehow, that analysis gives 2 times 1 minus 3 over p, the exponent for p greater than 2, instead of 2 times 1 minus 2 over p. Okay, so that's a gap there. Okay, and more recently, I improved the lower bound for p smaller than 2 to n, from square root n to n, but it's still weak. And also, David and I improved the lower bound for p greater than 2 now to the bound that we thought correct, which is n to the 2 times 1 minus 2 over p, which matches the upper bound when p is an even integer. And but however, so this bound is basically using the same hard instance, but actually the analysis is more elementary, and somehow it's tighter. Okay, but we actually think the lower bound for estimating p norm is n squared for p not equal to 2. As we see in the bit complexity case, that p is an even integer is always a special case. And we think that is the case here. The actual lower bound is n squared instead of 2 times 1 over 2 over p for general p for not integer. So it should read for p not an even integer. And that's our conjecture, and that is for this problem. Now this problem has somehow a small application to the lower bound of Oblivious subspace embedding. In this problem, you're given a t-dimensional subspace T, and you want to design a random matrix phi such that phi preserves the norm for all x in that d-dimensional subspace with good probability. Now you can rephrase this expression a little bit. Previously, Nguyen and Nelson showed a construction of phi that has d squared over epsilon squared rows, and they showed that this is also the tight bound. Okay. Now you can rephrase this a little bit, and you can take a orthonormal basis in that subspace, and now you replace x with u times x for x in a d-dimensional space. Now, from the expression here, you can deduce that the operator norm of phi times u is approximately the operator norm of u. Okay. Now, this condition is somehow weaker, so the lower bound that they proved do not hold anymore. Now we can use the similar hard instance as in the Schatten P norm to show that the lower bound actually still hold, which means that estimating the operator norm of a matrix is as hard as designing a Oblivious subspace embedding matrix. And furthermore, our lower bound works for any estimator. It doesn't need to be the operator norm. The estimator doesn't need to be the operator norm of phi times u, but it can be any function of phi operated on u and u, any linear function phi. So that is all my talk. Thank you.